Okay, so we're going to officially start the formal part of the webinar, and I'll note that we are recording this to post for people who couldn't attend the webinar. So if you are on video and you don't want to be on the recording, you might want to mute your video if you don't want your audio on. I'm just letting you know that. And also Erica may mute you to improve the audio quality while we're presenting. So please make sure you can find the chat box to ask questions. Erica's monitoring that, and we'll be trying to respond to you interactively that way as well. If you do need to interrupt us, though, you can unmute yourself and talk to us if you're having trouble understanding, or if you're having some technical difficulties and want to let us know by audio. I want to welcome M. Kincaid, and I'll let, we're just getting started right now. Okay, so I'm going to hit the present button here. Welcome, everyone, to the ExoLab Educators Community. I'm Mary DeSalt, and I'm the project director for this experience, this set of learning sessions around using the Laboratory for the Study of Exoplanets in your classrooms. I want to introduce you to the rest of our team. Lori Gould, who will be talking to you in just a little bit about the original background and goals for the ExoLab, is the principal investigator and the primary developer of the front-end interface that you see and that students use. Erica Wright, who is the person who's communicated with you about this webinar, is going to be our community coordinator for the ExoLab Educators Community. And she, as I said, is monitoring the chat box, so if you have questions. Frank Sinkowitz, who may be joining us later, but he is our telescope engineer. And so he often will be able to answer questions about the telescopes that are collecting the data for the ExoLab. And there's actually a picture of them in the upper right hand of this slide on the screen. There's a picture of them in an environment which they very rarely are. It's very green. They're in Arizona, and it's rarely that green. So I think it was this picture was taken during a very rainy monsoon season. Aladdin Ibrahim is our IT specialist. He does all the back-end database programming for the ExoLab. Harry Houghton is an education specialist with our team, and he's going to be developing some new video tutorials for you and your students in using the ExoLab. I want to mention that our team also includes scientists, grad students, postdocs, and researchers here at the CFA and at partner institutions who are kind of joining us on the online forum to answer questions. And we also have a few opportunities that will come up in the future where you'll get to hear from the researchers directly about their research questions and how they're studying exoplanets. And of course, the team also includes all of you, and we have some kind of master ExoLab educators who are joining this online community to really give you their insights about how they've used the project. And online right now is Jim Kernahan, who is one of those mentor educators for the group. So that's the team. Overview of what we'll be doing over the next 50 minutes. I'm going to give you a little background, a bit of background and goals for this ExoLab Educators Community project, which may be calling the EEC from now on. I'm going to introduce you to the online platform for continuing our discussions. Then Roy, the bulk of the webinar will be Roy giving giving a background and an overview of the ExoLab. We'll have a Q&A period at the end, but we really want you to ask questions throughout. Use that chat box, and then we'll end by next steps. So I want to, the context of starting this educators community, this EEC, is that the project, the fundamental goal of the project was to enable authentic science in the classroom. And we worked with a group of field test teachers, a couple of which are online now, 2 years ago, and got a lot of great insight from them. In early 2015, or mid-2015, we kind of launched the ExoLab for teachers to sign up and use on their own using the teacher guides and tutorials. And one of the things we've really found is that a big benefit comes from being in communication with teachers, and a big benefit for teachers is having direct access to the development team when you have questions and having opportunities to ask about different elements of the lab, and having opportunities to share strategies with each other. And that was a huge benefit during the field test phase, and we wanted to continue that effort. So the Arthur Vining Davis Foundations generously funded us to establish this online community portal, to offer this series of webinars, and to provide you with opportunities where you can interact with other educators who've used the ExoLab many times, and scientists to help enrich your classroom. So that's kind of the context of why we're starting this webinar series right now. And we're so happy to have you all here. And so without further ado, I'm going to stop sharing my screen and have Roy share his screen to give you an introduction and background to the ExoLab. So this is where you cozy up to the to your screen, Roy, and open up your PowerPoint.
But Jim is laughing at me. Okay. Hi, everyone. Thanks for joining. I'm just going to give a brief overview, so a little bit of background about the project.
I need to help you here. They aren't seeing what you see.
Oh,
Here we go. Share screen. PowerPoint. There we go. And now.
Go to slideshow.
Oops.
Oh, that's good. Oh. Thanks.
All right.
Great. Well, this is a project that that began with the grant from the National Science Foundation a number of years ago. The NSF was really interested, as you know, in developing authentic science inquiry in the classroom, especially that's aligned with the next generation science standards. And this project, the hunt for to detect exoplanets, is really, it's much richer in science practice than we had imagined. I want to just take a few moments to give you the context of this. So this first image is a photograph of you. I don't know if you can see yourself here. There you are with all your friends and family. This photo doesn't do justice, and that's the little planet Earth, that dot. So this picture was taken from, obviously, from the planet Saturn, from the Cassini spacecraft looking back at Earth, and it's about 800 million miles away. And the sun is hiding back here behind Saturn, and that's also about 800 million miles away. So if you imagine that you were an alien who had just made it into the solar system, you had passed the 3 outer planets, Pluto, Uranus, Neptune, and you had just arrived at Saturn, you'd see this little dot, you would say, maybe that's another planet, but you'd have no idea that there was life on it. from this image. So 800 million miles away sounds like a lot, but the nearest solar system to ours and the nearest exoplanet in it is about 1 million times farther away than Earth is in this photo. So that means that if you could take an image of that solar system, the exoplanet would be 1 million times smaller than the dot that you see here. And the sun would be 1 million times smaller than you see here. The planet would be 1 million times closer, so it would really be hidden right next to its star. It would be 1 million times closer to its star. And both the sun, the star and the planet would be 1 trillion times fainter than the dot you see here. And that's because the brightness goes as the square of the distance, so it's 1 million times farther, it's 1 million times 1 million fainter. So you would think, oh boy, that's an amazing challenge. And indeed it is, but in fact it is possible to detect exoplanets, as you're going to do this week if you haven't already done it. I just wanted to remind you how the field itself has exploded. I mean, this is certainly the hottest topic now in astronomy and astrophysics, and one of the great frontiers in all of science. Everyone is poised to discover the first habitable planets and the first signs of life on those planets. And the first of those has already happened. There are now a handful of planets that are in the habitable zone of their stars, where they're not too far, so it's not too cold, and they're not too close, so it's not too hot. It's just right. So, and you can see, if you look at this chart by year, it shows the number of new planets every year. And so, there was a trickle of planets and more every year. And then suddenly in 2014, 800 planets discovered. That was from NASA's Kepler mission, which is staring at 100,000 stars and has found already 2,000 planets around those and another 2,000 more waiting to be confirmed. And those planets are not like anything in our solar system, not like Earth. There are planets that are darker than any planet known. Crest 2 is one of those. Some of you may have looked at Crest 2 already. Darker than a lump of coal. No one knows why. There's a water planet that's basically, it's an ocean world. It's just water all the way down. And it's, unfortunately, it's close to its star, so it's very hot. You wouldn't want to be a lobster on that planet, or anything else, actually. There are planets, as you know, with 2 suns in the sky, so they orbit 2 stars at once. So they have 2 sunsets and 2 sunrises every day. There are planets that are falling into their stars. There are planets that we can see in the process of being formed around there, just from the huge disks around the stars. And we can see the paths that are being traced out. So we're really seeing planet formation in all of its stages. And what astronomers are realizing is that their old theories have just been thrown out the window. There's almost no long-held belief that hasn't been thrown out the window about what kind of planet can form where. So anything goes. And the most exciting part of this, in a way, is the discovery of the Earth-sized planets to date, based on the actual Earth-sized planets that have been found. Using that as a statistical sample, it's estimated that there are 1 billion Earth-sized planets in our galaxy alone, the Milky Way. And that's just a huge number. Now, that's Earth-sized. It doesn't mean they're all like Earth, because they may not have an atmosphere, they may not be in their habitable zones, but it's estimated that at least 16% of those are in the habitable zone of their stars. And basically, there's every opportunity and every hope that within the next 10 years, possibly even sooner, astronomers will detect the first signs of life on one of those planets. Now, as you probably know, that quest divides into 2 parts. First, you have to detect another world, and that's what has been done now. And then the second part is you really have to tease apart the light from the star and planet, and basically use a spectrometer to see what the planet is made of, what's in the atmosphere, what's on the surface. And that, of course, requires a lot of light. You're spreading it apart in a prism, so you need a lot of light. And so that's something that we can't really do from the classroom. It can only be done from the big space telescopes and from the giant telescopes on the ground, which are in the process of being built. One of them is the giant Magellan telescope that the Smithsonian is part of. I just want to go to the next slide. So clearly, this is one of the great frontiers of scientific discovery. And the idea is that you in your classroom are really working in parallel with what scientists are doing at the frontiers. We don't want to try to detect new planets because that's extremely time-consuming. But this project has confirmed tentative planets. So, and what will happen in the future, in the very near future, as more of these projects come online, is that there will be a lot of exoplanets that will have been detected by robotic automated telescopes with no human anywhere in the loop. And then what will happen is that people will have to, check back on those planets, on those stars to see, do they have a planet orbiting? Okay. Now, the other big excitement for us is that this laboratory is, we think, one of the best ways to get practice with the practices of science. And in particular, creating models, gathering, displaying, and interpreting data, and drawing conclusions based on evidence. It sounds sort of like a laundry list from NGSS, and it really is. But the thing that's very exciting about it is that this is one of the few projects, I think, where students can actually develop their own models. They know enough to develop a true scientific model and then test it, and then actually gather data and test it. And also, that turns out to be addictive and very, there's something very satisfying about it. So let's go to the, let's go to the site itself. So we're going to do it on
the right-hand page, already opened up.
I only
go to
shared
the. Oh, we're going to go on Chrome.
Yeah.
So, right.
Let's do this.
Same Chrome open already.
This. Why are we? Oh, sorry.
Oh, sorry.
I didn't
Yeah,
want that.
we don't want Firefox.
Thanks. Where are we? There we go.
Good.
So, share screen. Come on.
You shared.
Right, but I'm not able to pull this in. Okay. What is going on?
Can I help?
Yes.
Share. Right. All right.
Okay, so we're at, can you all see the laboratory homepage there?
Yep.
Good. Okay, so we're going to go to the lab now. And I'm not going to go through the whole lab. I think this is something that either you've already done or it's something that you will do this week as you go through it. And it's so much better to do it yourself than to see other people demoing it. And there's a lot in here. So I just want to give a sort of a logical progression to what's in here and why, and also maybe give you some feedback on what we found from working with other classrooms previously. So we would start in the modeling lab, and this is the place where we want to develop a model for what we would expect to see if we measure the brightness of a star over time, and the star has a planet orbiting it. We can only detect we have nothing else to measure using these telescopes except the brightness of the star. And yet it's amazing what we'll be able to tell from it. So let's see our model. I'm just going to go to the page where this model, where we can interactively develop a model, and the students can do this at their leisure. So as the planet passes in front of the star, obviously it's going to block out some of the star's light. And I'm going to try to draw here in this shaded area what I think we would measure as the planet goes around. And I'm going to say, well, I would say it would start blocking out as the planet makes it across the sky there. Oops, what am I doing here? I'll just start over. Thank you. Okay, I think it would start blocking out the light, and now it's sort of plateauing out. And then as it leaves, obviously it'll do less, and now it's back to its baseline like that. And you can, with this model, you can change the size of the planet if you like, or reduce it and so forth. The model lets you construct your own solar system. Now, what do students do? We found that every student can actually draw this qualitative graph. And when we ask them to explain how are the features of their graph related to this visual model, they explain it very well. They say, you know, it's blocking out some of the light, that's where there's a dip. They use various language to do it. And we found that even ESL students can draw, even if they have trouble verbally, they actually are great at drawing the right graphs. So we're pretty confident that students will get this. There is a quantitative part to this. If I stop the planet, there's the whole issue of how much light does it block out. And that's going to enable us to tell how large the planet is. That's something very important if you want to find something the size of Earth. And the bigger the planet, the more light it will block. And obviously, the deeper this dip will be. But how would you predict that? And we found a sort of bimodal distribution. There are some students who are very comfortable with the math, and they recognize there's a circle here, a disk representing the planet and a disk representing the star, and the percentage of light is basically the percentage of their areas, the ratio of their areas. So, but many students don't know how to really set that up. And, you know, it was that after all, they know that this planet is not a disk, it's a sphere and so forth. So there are many other factors that might confuse them, but you can step them through it, and the modeling lab steps them through it. And they would basically save their work here. And then when they come back to the modeling lab, they'll see their model as they left it. And they save their graph and they save their written work. All right, let's go on. So they have a model, and the model says, well, there's a straight line, then there's a dip down, there's sort of a plateau where the planet is there, it comes back up again, and that happens periodically. Okay. So let's go now to the telescope. Let's look at our target star. So we're going to request images from the of our target star. In this case, tonight, there's the transiting planet around HAT P36. That's the Hungarian Transiting Planet Survey. Lots of countries now are doing this. And this tells you the hours that are available to watch. So 2 a.m. in the morning, and then here are the minutes showing you all the available hours. So you can take as many of these as you want. And then you would take an image just by clicking here. And then tonight at your requested time, the telescope will point to the star, take an image, and then tomorrow morning, it'll be waiting for you here in the image lab, which I'll go to. Okay, so here's the image lab. We're under Analyze Images, and we're going to step through these 3 main areas. Show My List, I'm going to log in as Mary.
Good.
So when we see My List and I'm Mary, here's actually all the class images that have been taken, and they go all the way back, as you can see, for a month. Okay, and we're going to do, let's see, it was right up here at the front. Oh, well, first I want to say, when we look at our image, you'll see stars and everything, and the sky in the back will look black. But it's not really, and that's because there's noise coming from the telescope chip itself. So I'm going to show you a dark image here. This is dark image, and you'll notice down here, it tells you the brightness of every pixel running from 0 to about 4,000 something. And you can see that although it looks black, it's not. There's noise there. And we want to subtract that from all of our measurements. So I'm just going to hit subtract dark. And from now on, we won't have to worry about it. Now it really looks dark. And look at that, the brightness is 0. So now we can go back to the list and open up an image. And there's our star field. How do we know where our image is? Well, we go to locate target star. And there's a chart, the old-fashioned kind that the old navigators used to use. And we'll just go over here. Can you see how this pattern here matches this one here? So this is fairly straightforward to match like that. See how they all line up like that? This is critical, and it's the one place where your students are likely to go astray, because if you take your chart back, it's hard to find your star again. They all look alike, don't they? But they're not. So I'm going to actually do this with the star chart in place. You can actually measure your image through the star chart, because we're measuring the file that gives rise to this, not the actual physical thing you're seeing on the screen. So if we now measure the target star, let's see, here's T for target. I've centered it. You see that yellow circle off to the right, and I click, and there's my measurement of the target. So I want to get it right in the center there as much as I can. And now I'm going to go to the comparison star. I click on the box there, go in here, measure, boom. Go on the second comparison star, which is over here, boom. And now I'm going to measure 2 areas of the night sky, these dark sky. That's because the night sky itself is not dark. It looks dark, but in fact, you know, there's that zodiacal light and dust and light from Phoenix and from Tucson and all of that. So you want to get rid of it. And I'm going to just find a spot near the stars where there's no obvious star. And I click on it, find yet another one there just to make sure. We have a second one, click on it. And then we can calculate and record. And what we're doing is just averaging the comparison stars and the night sky background. And we're subtracting the night sky from everything. And then we're just taking the ratio of our target star to the comparison stars. The comparisons won't change over the course of the night. They don't have exoplanets that we can see. So if there's an exoplanet around the target star, we'll see that ratio between the two start to change over the course of the evening. And then we can go to our view data, and you'll want to go back and do this for lots of images. And Mary will describe for you the protocol that you'll be doing this week. If we go into data, you can see that you're actually collecting data. I didn't click anything, so these are all prior data that Mary has taken. And then if we go to graph brightness, we'll see the graph of these data. And what is this graph? So it shows us the relative brightness of our target star compared to the comparison stars for each of our images. So every dot is a different image, and you can see it progresses over time of night. So we're looking to see, as time progresses, what do we see? Now, what we see here is looks like an absolute mess to me. I mean, you know, if somebody said, oh, that's a planet. But it's not Mary's fault. These are the data. These are what we get, okay? This is what we get. And there is, in fact, a transit in here, but we don't have enough data yet. And that's going to be part of the thrill. I think it's really thrilling to see a curve take shape as more and more data are graphed. And so you're seeing the natural scatter. We'll see some reasons for why there's that scatter in a moment. And then you can look at the whole class's graph, but I won't do that now. So we're just looking at Mary's measurements.
And we aren't looking at the whole class because we're going to ask you guys to be the whole class during the next week. And so I'll talk about that at the end of the webinar.
Right, and you can move this graph around if you will. You're not changing the data at all, just the way you display it. Now there are a couple of things here that will help you interpret the graph. I mean, either you're going to see a transit dip or not, but one of the interesting parts is components. Remember, we took 5 images, 5 measurements, the target star, and that's shown here in green, and then the 2 comparison stars are in red, and then the night sky, the background night sky. And of course, this shows the individual measurements. And it gives you a better handle on what's going on with your data. And this is good because they're pretty, there's nothing untoward. See this way up here? That's me. I took an image of the wrong comparison star, and measured the wrong comparison star. So you see that right away. Notice that this is lower, the night sky is lower than any of the other measurements. That has to be because the night sky adds to all the other measurements, individual measurements, and that's why we subtracted it out. Something else you can see here that's interesting is that the night sky is relatively low, whereas your target star is way up here, nice and bright, whereas the night sky is relatively low. That means there's good signal to noise, right? In fact, the signal to noise is just whatever, here's the signal, it's the brightness of your star going up here. And here's the noise, which is the background. And so, you can see that you can clearly see the signal from the noise. If there was a lot of problems with your images, cloudy or something like that, that background night sky would be right up here and you'd have very low signal to noise, that you'd have high noise, relatively low signal. Okay, and I just want to show you the altitude here that shows you where each image, where the star was in each image during the course of the evening. And here you can see it's pretty high up, certainly until the very end. And if the star is too low, then you'll start to see a lot of scatter because you'll be close to the city lights, you'll be close to the more air mass and so forth. We'll see that in a moment. In fact, let's just take a quick look at that now. Here on page 5 in this graphing is a little cube. It shows you all the things that can go wrong and give you a lot of scatter. Here's moonlight. I'll double click on it and I get a graph that will illustrate that. So something's happening here at the very beginning of your transit. It looks like there's more scatter here. And if I look at the, what am I doing here? Oh, yes, well that was, let me just cycle through, oops. So in fact, this here you can see the noise was very, very high. And this is because when this star was observed, the moon was very high and it was blocking out everything. But notice how it gets darker and darker and darker, and then it levels out. And this is where the moon set. So if it were a moonless night, everything would be down here and there would be a very good transit. But we can expect a lot of scatter because we see that that the moon is up, the night sky is very bright. And so, yeah, you can look at other factors here as well. There's finding the wrong star, what does that look like? There's what's the role of the atmosphere. If you're too close to the horizon, you'll see what happens there too. Okay, so we've got our class has their curve. There it is, my graph. Doesn't look like much. But we're going to now log out and go to the data lab. I'm logging out because I want to just see, a clean transit here. Again, if you saw only a few data points from here, you would have no idea what was going on. So this is one that a class took, and it was a good night. And I'm going to just go to the relevant page here. This will step you through it. But what we want to do is extract from all these data, we want to extract some information about what the planet was like. So first of all, actually, let me just go back. I mean, would we say that we had found, had we detected a star here, a planet here around this star? And certainly looks like it, because here's the predicted transit time. And so now we see that not only is there this dip, but it's pretty much centered around the predicted transit time. It's sort of, we see what could be the baseline here and here, and then it's coming down, and then there's some kind of base here where it's in front of the star. The planet is transiting. So let's use this curve fitting tool. So we would like to say, well, what is the curve which best fits these data? That's similar to the curve we drew in the modeling lab. And so we have a curve fitting tool, which you can move at your will, and you can basically try to fit it to the curve. And the best curve that you can make, well, it's one that you'll do by eye, but there's also another little aid, and that's we're scoring. We're trying to minimize the distance of all the data points from the curve itself. So if I move the curve way up, you'll see the score goes way, way up. So we're trying to get the least score possible, and that is the best fit of the data to this curve, the best fit of the curve to the data. Okay, and it'll be something like this. And now, what can we, before we say this, what can we tell from it? Well, we're seeing where the estimated baseline is at around 1.09 something. And then here's the estimated dip level, 1.07, which is down here. And remember, these numbers are the relative brightness of, we actually don't want to use that when we publish the data. So when you publish your data, we're going to translate this to just 1. Whatever you say is the baseline, we're going to say is 1. And then whatever this is, it'll be proportionately less than 1. And that way we'll be able to superimpose data from lots and lots of schools, and that way you'll be able to see a much sharper curve. Okay, so here your students will be writing how does this compare to the planets in our own solar system. They'll be stepped through this, and they'll be gathering various data about this planet and figuring out how large it is, for one thing. They can actually figure out whether the orbit is tilted or not. I mean, there are lots of things you can tell just from the data you get back. And then they would type their here. And now you'll be looking at students' work, and from their best fit curves and from their comments, as Mary will tell you later, I mean, we're really asking you to excerpt and to really summarize that and publish. So you can only publish from your own page. So you'll want to actually reproduce whatever the student's best fit is here, and is the lowest score, and then write a representative sample of comments. This is what the class thought, this is our class deduced this about the planet. And then just hit save your work. And when you save your work, it's saved to the database. Students' work is saved to the database, so if they come back, they'll see their curve and whatever stage they were in, and you can continue from there. And then I'm just briefly, we'll go to the community page. Well, we don't have to do that now, actually. I'd rather make sure that questions come up. And, but that's basically the long and short of it. So every transit curve will be different. And of course, every condition of, every night is different. So the data you'll be getting back is absolutely unique. And it's a challenge. So good luck.
Right, so I want to kind of take a break and ask if people have questions at this point or want some more details about things you've heard Roy say that you've either experienced something different or you're wondering what's going on. If there's any questions, you can either unmute yourself and ask them by audio, or you can type in the chat box. And okay. So I'm
sorry, I was going to ask a question.
Oh.
Is that okay?
Yes, of course.
Okay, so we're doing this.
I don't have that.
Maybe I should type it.
Oh, audio, right. She's listening.
Okay. Okay.
There we go.
All right.
Yep.
We had used this earlier this year, and there was just one of the parts where they were moving their graph. I don't see it on this page, but it's like when they have to they're trying to find the best fit. And there's some numbers that were at the bottom that they had to.
Yeah, it's on this page.
Oh, the current score. Is that what changes as they move around?
Yes, here, I don't know if you can still see it. See the current score? It's kind of faint there.
Okay. And are they just trying to get the lowest, the best? I just remember.
Yes, so where it says my best score, that's the best fit that they've gotten so far. So here, that's a pretty good fit. But if they go off and they say, oh, I don't know, I have to go back,
Okay.
you can just go to reset to best, and it automatically takes the curve to where the student had the lowest score
So
on their.
Hold on 1 second.
the website is calculating and figuring out whenever that it just comes up with their best score then.
Yes, it's all that's computed,
Okay.
so they don't have to. And it's yeah.
Okay. Okay. But it'll only show that if they click to reset to best as they're playing around with it.
If they're playing around with it, it lists their best score down here, but they may have a hard time finding it again.
Right.
So that's why we have this feature where if they just click reset to best, this is the one that gave them, this is the curve that they had done, which gave them the best score.
Okay. And they might have gotten that just by moving their line around and not even realizing it.
Yes, exactly that.
Okay.
And
Thank
normally,
you.
scientists do it all by computer, but it turns out it's tricky to do it just by computer. And so doing it by eye is actually a very good way to get the best sort of start on it. Yeah.
But what that score is doing is it's the sum of all the distances of the real data from the model. So what you're trying to do by eye is to get that baseline and that dip and those slopes to be as close a match to minimize the variation from the model of your data, and so that's the quote unquote best fit. So this is a way of understanding best fit. You know, there are automated algorithms. Your Excel will draw a best fit for you, but what is it doing? Here, you are the score is giving you an indicator of when you've identified the baseline brightness and the transit depth brightness that best fit your data.
So
And you then use those values to actually, somebody asked about, can you get to the radius? This, what we're gonna focus on the data lab in a later webinar, but your data can be used to calculate the ratio of the planet size to its star. So you can calculate the radius of the star. You cannot get its mass, however. Somebody asked about that. That's because it could be a big star that's fluffy. Or it could be a small star that's fluffy or a big star that's dense. So you I think I said that the opposite way. But anyway, you can't know its mass without knowing using another effort that scientists use, which is this wobble method, radial velocity.
And there is, I might just say one other
Yeah.
thing about that. Your data can help scientists, can actually help in some cases to determine the mass of the planet because, for example, if this planet is orbiting, if there's another planet nearby, it will actually change the period of the planet slightly. And so these transits will happen a little bit too soon or a little bit too late beyond prediction. And so that's why the data set that you collect, and if there's another planet, and somehow that interaction allows them to to estimate the mass of both planets. It's very involved, but it shows that the scientists are basically trying to squeeze everything they can out of the data. And in fact, that's one reason why it's really good to have multiple records of transits of the same planet.
Okay, I want to answer some of the questions that have come through in the chat box with regard to saving the work of students. You as a teacher with an account have some features, and we're actually just adding some new features in your account under the Manage tab, which you don't see on the screen right now because Lloyd has signed. This is as a student, he hasn't logged in. And one of those is a tab where you can see what your students have written in all the fields. The other, with regard to the visual aspect of, I mean, yeah, actually, I guess so there is a way to get to your students' data, and we'll be going over that in webinar 3 or 4. I'll show that schedule a little bit later. The other thing is you will be able to download all your students' results as an Excel spreadsheet, so you can use that to, kind of score or do grading or whatever you have to do. But you'll be able to collect that. Let's see, other questions here. With regard to technology and Windows 10, the Chrome browser, the key thing that works best with this is the Chrome browser because it has a built-in Flash, and all the data tools are written in Adobe Flash, and the Chrome browser handles that much better than Internet Explorer. In fact, don't ever try to use Internet Explorer, but the Chrome browser will work best. Let's see. The images in your image lab are only available for a month after the telescope took them. But your data, your graph stays there forever. And you also can download, you could actually go to the MicroObservatory archive and download all the FITS images. And actually we have a mentor who's going to show you in a later, actually on the community, what he's been doing, downloading the data and then using some other analysis with it. Jim, Safari, it really depends on the combination of operating system and browser. So some versions of Safari it works and some it doesn't. Depending on updates. Let's see, other questions here.
That's about the sample set, and that's the publishing.
Let me put in a sample set of what students
He was talking about the publishing tool. You get an opportunity to put in. The teacher should put in what they say.
Okay, I'm still not understanding Brad's question. So
Where it was mentioning putting in a sample of what your students say. So the teacher is the only person that can publish, in which case you'll want to write in the right-hand box that you see on screen here yourself, a sampling of what your students or your class is saying, so that when you go to publish, that will be displayed with your data that you publish.
Yeah. We're actually going to go over that in detail and how to do it as a teacher in webinar number 3.
Okay, yeah, that was my question, was how to get that data.
We'll illustrate that. Great. All right, before we go, one thing I forgot to do, and I'm going to share my screen now, is to show you the online community that Erica is going to give you login information, and you'll be able to get to tomorrow, or at least by the end of the day tomorrow.
Yes.
So there's a link to the online platform for us to continue communicating after this. It's on the For Teachers page in the lab, and I'll click on that. And you will log in. In fact, I have to log in again. And Erica will get you your login information. And so you'll see that there are some online discussion forums. These end up sending an email to your email inbox when things get posted, but you have the ability to specify whether you want that to come as a daily digest or whether you want to see all the emails. You'll see that the first thing we'd like you to do once you get your login information is we want you to introduce yourself in this forum. I've introduced myself here, and you can just reply to this and introduce yourself. I want to actually, thanks, Roy. Roy has to go. We're about to end, and he has to go early. So thanks, Roy. Let's see. So let me go back.
Before you go into that, just so I don't confuse people.
Yep.
I'm going to start sending ExoLab accounts and passwords right now.
Okay. So Erica is about to send you in the chat box or information, because we have some homework for you, which is that we want you all this week to be our students, and we've created a classroom account where you guys can be the students, and you'll log in. Erica is giving you these usernames as teacher, whatever she says, and then you'll do the password that she gives you, and then you'll and then you'll be in as a student, and we are going to ask you guys to measure, and she's also giving you, we're going to ask you guys to measure that WASP 43 from the other night, 328. So Erica is giving you a username, a password, and information about the set of images for you to make the measurements of, because we'd like to, at next webinar, take a look at that data, and only by doing it yourself as a student and seeing how all your students' data comes together will you really experience some of the issues that come up with using it with students. So she's giving you information for an ExoLab workshop account. And meanwhile, tomorrow, she's going to send you login information for this online Moodle platform where we're going to continue to communicate. All right. So in fact, this webinar is right here. We've kind of provided the overview. And so the assignment, and really when I say assignment, this is just something, if you are able to do this over the next week, it would be great because it would help our webinar next week. If you aren't, don't worry about it. But it's your turn to be the student. And so using the teacher account that Erica gives you, you're going to make 5 star measurements. and basically she's giving you the time at which you should make those measurements. And if you want to make more, you can. If you only have time to make one, that's good too. We're going to take a look at our collective data next week in next week's webinar. And again, all these webinars are recorded, so even if you can't come to the webinar, you'll kind of see the results and see what happens. Okay, did I get rid of confusion that way, hopefully? And we have some more questions that have come up, so I want to make sure I'm getting to those. Yeah, last two, right? So the time that she's giving you is when you hit show my list, you see that there's WASP 43. It was taken in 2017 on March 28th. And the universal time of the data set started at 04:09:29. And so we take images every 3 minutes, 09, 12, 15, 18, 21, 24, 27. So she's giving you some number like 27 or 00 or 09. And so what you want to do is if you got 09, you want to measure this image. You want to go to this image. And you want to go to 0609, right? This image. So we're trying to spread everybody's images out. That's what that's about. Okay. So next steps, do it yourself. Use your account that Erica just sent you via the chat box. Tomorrow, she'll send you login for this online community that I just showed you. And we hope that you'll join us for the rest of the webinar series. And here's what the webinar series is for the next few weeks. Jim, with regard to is this going to be enough, we have people from the 3:30 webinar who are also doing it. And if you want to do more than 5, choose another time period that you don't see on your class graph. And
48 and 51 haven't been taken.
40 and
54 and 57.
54 and 57 are the times that have not been taken. So if you get through all of yours and you want to try another set, do the 54 minutes and the 57 minutes. So next week, yeah, definitely extra credit. You do not have to do this. Next week, we'll be looking at that image lab in detail and examining other examples of student data and what can happen depending on the quality of the data. April 12th, we'll be going into detail on using that data lab and publishing class data to the community database and to the community page. Because by publishing your data, you are actually helping us as we get more data. We have the possibility of making discoveries about the planets using that data, but it's very helpful to the community. April 17th, and April 17th and the 24th might be switched, but at any rate, we have a grad student, Shani Nava, who is studies exoplanet atmospheres, and she's going to do a presentation about her research. And then we're on the 24th, we'll be asking for strategies from those who've been there, tips and tricks. And Jim, I'll be in touch with you about that one, and maybe you too, Jackie. So I think we are at the end of our planned presentation. If there's any other questions, or you want to again come off being muted and make yourself heard for the end, we'd love to hear from you.
Okay, looks good. I'm excited to try it myself.
Yeah, thanks for taking the time to put this on for us. Yeah, very few people actually give support, so thanks.
Great.
Yeah, really appreciate it. Thank you very much.
Happy to be here for you all.
And the other thing I want to point out is we really hope to learn from you how to, what kinds of supports would really help you. And we will be putting them on that online platform, which is open to any teacher in the future. And we have hundreds of them using the ExoLab, so that your contributions and your ideas will get to other teachers and will really help. All right.